Alright, so I'm gonna try explaining things. Let's see how well this goes. So, memory allocation. Your computer has a lot of memory, and you can normally treat it as just a massive array. It's like a long list, and within each unit of allocation, it's called a byte. You should know what a byte is. You can store something. In this case, everything in computer is zeros and ones, but let's just consider it to be something like 1 to 600, because each unit, each byte can store different values. 600 actually isn't a valid value, but let's keep it there for now. So let's say this is your memory M, and you have a program P that wants to write and use some memory. For example, P could be something simple like let there be an integer x equals to 100, and then we can do x plus equals 20. This means that we add 20 to x. This is already a program itself that requires a few things. If you've read up on computer organization, you know this compiled into assembly. It'll do this thing, it'll allocate a register by fetching the x variable from memory. So let's say the memory is, I'm writing MIPS code because that's what I learned. It could be something like a load word from load word to, let's say, a temporary register 0, and then your memory address could be, let's say 100 is stored at memory address, just make this dot dot dot, 100 is here, and then we want this to memory address, let's say 64. So this would be your register, I forgot how this goes. I think it's like 0 bracket 64, something like that. Is it? It's a register access. Normally it would be something like you would like load intermediate the number 64 into, you load like the T1 you load like the number 64 into a variable, and then you call the load intermediate function to get from the variable there. So once you have this variable, and once you want to fetch the variable, then you can use this variable in your instructions, like let's say add I t0 20. This adds 20 to this variable, and then we can write the variable back to where we want it, which is here. Yeah, so this is the code. But you may realize 64 is basically a random number we just came up with. Sometimes we don't want it to be 64. Sometimes it could be, let's say like 300,000. Your current memory is very large. It is up to like billions of bytes. So 300,000 isn't that far off. Hence, how can we have a memory that can address so many different positions? Not just positions, but programs as well, because, you know, we are living in a society where we have multi-process operating systems. Each operating system has to run multiple programs. How do we split this memory among so many programs? Today we're gonna do this thing called contiguous memory allocation. So the word contiguous means it's like one long continuous stretch. So we will assume that each program will get one continuous chunk of memory. So that in this case, your memory M doesn't have to be M. It's the memory M of your program P. And each program thinks it has some chunk of memory. And in our code, or in our OS, each chunk of memory is indeed one chunk of memory in RAM. In this contiguous memory allocation, it could be split into multiple parts, but for now, it's just one chunk. So let's see, this is our entire memory M. This part could be memory for P, this part could be memory for some other program P2, and this could be empty, so on and so forth. How we can determine this There are multiple ways to do so, which we'll go through first. So first of all, there's a naive method called fixed partitioning. Fixed partitioning means, surprise, you divide it into fixed partitions, which would look something like this. Each partition is the same size, and you can just put, let's say I need to store MP, I'll just put MP in a free partition. I need to store MP2, I'll just put it in a free partition, so forth. So you can see that the benefit is that it's really convenient and really easy to keep track of, because it's very, very easy to keep track whether something is empty or not empty. That's all you need. There's no need to see, oh, how much is it filled, and other bookkeeping elements. But again, that's also a drawback, because this means that you can only allocate this much memory at once. No more, no less. So let's say I have like MP3, which is only like very, very small. That's actually a very bad illustration. It might only need like this much space. Then what happens to this entire chunk of space? This is called internal fragmentation. So this means that it's gonna be this means that within our allocated partition or allocated memory, there is wasted or unused space. So you could say, oh, why don't we allocate fixed partitions? Why don't we just allocate each program the space that they need? Well, that's called dynamic partitioning. Dynamic partitioning is just having your memory, and then for each program you just add on what you need. So let's say MP needs this much space, or MP2 comes along and needs this much space, and MP3 needs very little space, so we just give it a little chunk of space, and it's not wasted. Perfect. But watch what happens if, let's say, oh, we finish the MP2 is cleared from memory. How do I clear things from the screen? Yeah, here. So let's say we finish MP2, that's empty, and now we have to run another very small program, let's say MP4. Now this is taken, and oh no, I need to run MP2 again. MP2 is like this big, so it can't fit in here, and so we have to put MP2 here now. So we have this chunk of space that is kind of wasted, but unlike the previous case, this is outside of allocated memory. We call this external fragmentation. So there's a key difference between internal and external fragmentation, and it lies in the fact that internal fragmentation is unused space within allocated memory, and external fragmentation is space outside of allocated memory. Alright, so we have these two problems. We have both solutions which don't work very well. It's embarrassing to call them solutions. So what can we do in this case? What's a good way to have contiguous memory allocation? Well, we have something called the buddy system that is introduced, and it's quite useful and kind of cool. Let's write that down. Buddy system. So what we do in this case is, let's see our memory here. Let's say I have MP, it's this big, and I don't want to use so much memory. So what the buddy system does is it splits your memory in half. And if you can split it in half again, and there's still enough space, it splits it in half again. And it does this until there's a small enough chunk of memory that fits your new memory chunk. This way it minimizes the amount of memory that's actually allocated, while being still able to fit the entire program into memory. So in this case, we split it once, twice, and we get this chunk that we can fit MP in, and so now MP becomes part of that block. Let me put that in there. Okay, so MP. Then let's say, oh, I have MP2. Let's say MP2 is a bit bigger and it can't fit either of this, so we can just put MP2 here. Let's say, oh, MP3 comes in. MP3 is very small, so we can split this part smaller, smaller, perfect, MP3, put it here. And then MP4, also very small, oh perfect, with next spot next to it, right, just the right size. And now you can see how this comes into play, because there isn't too much internal fragmentation, because we are splitting the blocks to as small as they possibly can be before putting the memory inside, while not having too much external fragmentation, because we can further split. We have enough space for large and small programs, such that the larger programs, once they're being freed, that space can still be used to store other programs. So let's say MP2 is freed. I'm not used to this. Let's say MP2 is freed. I'm gonna draw that back. Yeah, let's say MP2 is freed, and now we have this much space. It's immediately free space that can be used by other programs. And even let's say if we freed MP itself, this is still space that can be further subdivided to store smaller programs. And the cool thing about the buddy system is the buddy system itself, which I haven't talked about. So let's say this program is freed, and then this part is also freed again. So now we have these two sections here that are at the same size, and they're next to each other. And so here you might have thought, oh, there's a gap here, I can fit something in here. That's good reasoning, but in the system we don't really have an idea of empty spaces. We normally see things as a list, a linked list actually, of free spaces and the start location. This goes to another one, it could be occupied. It could goes to another one which is free. Yeah, this is just an example. But let's say we have two linked lists in a row that says, oh, both of these are free. There needs to be a way to combine these two, and that takes a lot of computational resource. However, in the buddy system, it's very simple. Let's remember that each of these addresses has an address. So let's say this would be, just make up number 000100. Let's say that one's 00000. I messed up. Let's say there's like one here, there's one here. How about that? Okay. So you can see how these are the same length because it's the length of a memory address. All addresses in memory have to have the same length. So ignore this part. This part is the size or the exact bytes within the block itself. I think if you don't understand that, you should go and read up on computer organization. This is not meant for you to understand, it's meant for me to explain. But this is the bit we are focusing on. This one has a bit of 1, this has a bit of 0. As you can see, these are complements. And the rest of this here is the same. It might be hard to understand, but if you look at it closely, since both of these are ways to describe an address, via this simple sort of observation, we can see that neighboring blocks of memory have a very similar structure. So from this, we can actually check very, very easily whether we should combine the two. So if the leading bits are the same, and the final bit before the offset of the memory is a complement, then we know that the two are buddy blocks. And when they are buddy blocks, we can merge them and create a larger block. And the buddy merging goes on and on until you can merge and everything back together. So that's the beauty of the buddy system. It's a very easy way to just merge and unmerge things, unlike using a linked list, as you can see there. Of course, the intricacies of the buddy system come with the implementation. For example, each of these partitions is implemented as a list of we have the index of k. Say k is 0, 1, 2, 3, 4, and each of k is a list of partitions with size 2 to the power k. So let's say this one is 6 bits, right? So this power 0, 1, 2 to power 2. So let's say this is an empty one. This is an empty buddy system. You have one partition starting at 0, which is 2 to the power of, actually it's actually quite large. It should be, wait, let's say this is 5. Yeah, so it's 1 starting at 0, because this entire thing is 2 to the power of 5 large, let's just say. And so let's say we need something that's 2 to the power 2 large. Then we can split this into 2, 0, and let's say 16, I think. Then we can further split 0 into 0 and 8. Split this into 0, 4. And now we can use 0 to store something. And we have 3 partitions here, which you can visualize like... that's not a fair visualization. You can visualize it like this. So now we have 1, 2, 3 different partitions, 1, 2, 3 here. That's how it's allocated, that's how it's visualized, and I hope you can see how precise and powerful this representation is. Okay, this has not been a very clear explanation, but there's a start to everything. Let's see how this turns out.